So in this video we're going to look at discrete random variables. And a discrete random variable is a variable whose value is a numerical description of the outcome of a chance experiment. So down below here I've got a tree diagram for a coin that's been flipped 3 times. And these are the outcomes of that particular chance experiment. And a discrete random variable takes these outcomes and replaces it with a numerical value. In this case, the numerical value here, which has the heading x, stands for the number of heads. We've defined a variable here, so this is my discrete random variable, x, and x is the number of heads in each of these outcomes. So this outcome here has 3 heads, so x is the number of heads, so it's 3, and it has a probability of 1/8. This outcome has 2 heads, so x is equal to 2 with a probability of 1/8. This outcome also has 2 heads, so its value for x is 2. This one has 1, this one has 2, this one has 1, this one has 1, and this one has none. And you can see here that I've got multiple occurrences of the number 2 and of the number 1. So I can actually use this x value to simplify this whole tree down a little bit. And that's what discrete random variables help you to do. So what I've done here is I have created a table. And in the table I have the first row is labelled little x, which is the outcome or the value of this number of heads. Okay, so x is the number of heads and this is the value 3. X is the number of heads, this is the value, the little x is 2 here. Okay, so our possible outcomes for x are 0, 1, 2 and 3. So 0, there's the 1s, some 2s and a 3. Now the probability that the number of heads is equal to this particular x value, 0, is 1/8. The probability that the number of heads is equal to this next x value, 1, is 1/8 plus 1/8 plus 1/8. So it's 3/8. And so forth for 2 heads, 1/8, 1/8, 1/8, and 3 heads, 1/8. So all of the outcomes that I have here are contained within this table. And so all of these probabilities here should add up to 1 because it contains every possible outcome that I had before. Now this probability that x is equal to x, that's how you say it, can be simplified down to just p of x, the probability of x. And so this value here, this 1/8, is the value of p when you substitute the 0 in for x. And this is the value of the probability. This is p1, this is p2, and this is p3. So this table that we had is what we call a probability distribution table. And we can take these p of x values that we've got here and we can define p of x to be a function of x, so that x is the variable. And we can plot that function with p of x as our y value and x along here. So p of 0 was 1/8, p of 1 was 3/8, p of 2 was 3/8, and p of 3 was 1/8. Now, we don't join the dots here because there is no x value between 1 and 0. There's no x as a half, there's no x as 3/4. So the x values that are there are the only x values that it can happen. And if you join that two lines, if you join the two dots together, what you're intimating is that you're saying that there are other values of x that exist. Every time you put a dot there, it means that there's actually a value of x down here, and it has a probability, and that's not true. Now, because we can only have particular values for x, x is called a discrete variable because it only has discrete or separate values. It's not continuous values. Now, the probabilities for p of x are determined by the outcome of a random chance experiment. And so that's how we get our discrete random variable name for x, because it's a discrete value, it's a random value, and it's a variable. So taking another look at this particular table, our x values can be any values at all because they're the outcome of the experiment. So we don't know what these values actually are, but we know that these values in the second row are in fact probabilities. And because they're probabilities, they need to be between 0 and 1. So you can't have negative numbers in here, and you can't have a number that's greater than 1. The other thing we know about this row here is that all of these probabilities should add up to give you 1. And this is the symbol that they use here. This is the summation symbol, and it's saying add up all of the p of x values for all of the x values. When you do that, it equals to 1, or simply this row adds to 1. So the sorts of questions that you'll get with probability distribution tables are, what's the missing value here? And so you would need to see, what do I need to add here to make it up to 1? You will have something like this where you've got an unknown in here, and they'll ask you what the value of a is. And to do that, you need to be able to recognise that when you add these values together, like I've done here, it's equal to 1. So collect your like terms. 7a is 1, so a is 1 on 7. And sometimes you'll even actually have a proper function that you use to generate the probability values. And so in this case, what we do here is we substitute in our x values one at a time. And then use the fact that this row adds to 1. So whatever the numerator adds to, the denominator has to be the same number so that it will simplify to 1, which means that in this case, each one of those k's is worth 57. The other thing that you'll be asked to do with discrete random variables probability tables is to find particular probabilities for a particular table. So for this table here, we need to find the probability that our x value is greater than 3. And so we look at our x values, which are up in the top row, our x values. We want our x values to be greater than 3. And the x values that are greater than 3 are 4 and 5. And so our probability that x is greater than 3 is equal to the probability of 4 plus the probability of 5, which is 0.1 and 0.3 from the table here, 0.1 and 0.3, so the probability is 0.4. The probability that x is less than or equal to 3, includes 3. It includes the x value of 3 and anything that is also less than it. So in this case, it's p of 3 plus p of 2. which gives us 0.6 when we add the two probabilities together. And of course, they'll ask you to find conditional probability. And you need to be very careful here, making sure that you remember that the top line is in fact the intersection of the two situations. So in this case, we're looking for values where x is greater than 3, which will be x as being 4 and 5. So that is our x is greater than 3 section. And we also want our values to be less than or equal to 4. And our less than or equal to 4 are the values in that blue rectangle. So the only section that belongs to both of those rectangles is this little bit here in the middle. So our top line for our conditional probability is in fact just 0.1, and our bottom line is what was contained in the x minus 4, which is all of these probabilities in this blue rectangle. So 0.2 plus 0.4 plus 0.1, which is 0.7. Which is 1/7. And finally, you'll need to be able to make your own probability distribution from a worded question. So here's a worded question that we're going to have practice with. The laundry basket contains 4 white socks and 6 black socks, and it's your turn to pair the socks. And to make it more interesting, you decide to choose one sock with each hand while keeping your eyes closed. Find the probability distribution for x, where x is the number of white socks chosen, and then find the probability that you pick 2 socks of the same colour. Okay, so the first thing we're going to need to do is to come up with all of the different sorts of outcomes that we can get. So we're going to be picking 2 socks, one with the left hand, which will be either white or black, and one with the right hand, which will be either white or black. And so even though we pick them at the same time, we're going to treat them as if we were doing them one after the other. So if we pick our first sock, we have 10 socks to choose from. So both of these probabilities are out of 10. Probability of white is 4 out of 10. Probability of black is 6 out of 10. For our second sock, however, we've already got 1 sock missing. So now all of our probabilities are going to be out of 9. Out of 9. And if we chose a white sock on our first choice, that means there are now only 3 white socks left, so the probability of choosing those is 3 out of 9. If we chose a white sock on our first choice, that means there are still 6 black socks, so that becomes a 6. The other way, of course, is that these 2 fractions should add to 1. If we chose a black sock first, that means there's only 5 black socks left, so to choose another black sock is 5 out of 9, which makes that one 4 out of 9. And so our outcomes are shown here, and I've also worked out their probabilities. So now what we need to do is we need to turn it into a probability distribution where x is the number of white socks chosen. So what we're going to do is classify each of the outcomes as how many white socks there are. So in the first outcome there are 2 white socks. In the second outcome there is 1. In the third outcome there is 1, and in the fourth outcome there is 0. And so now to find the probability distribution for it, I need to make a table. So here's the table. X values on the top, possible X values are 0, 1 and 2. Now all I need to do is to fill in the probabilities, and I take them just exactly from here. So the probability of 2 is 12 on 90, the probability of 0 is 3 on 90, and the two outcomes that have 1, I add their probabilities together to give me 48 out of 90. And the final question asks me to find the probability that you pick two socks of the same colour. So that means that you'll have either 2 white socks, which means the number of white socks would be 2, or you would have 2 black socks, which means that the number of white socks would be 0. So the probability that X is equal to 2 is 12 90ths. The probability that X is equal to 0 is 30 over 90. So the probability that we pick a pair is in fact 42 on 90.